Alright, continuing on from last time, we've just established this property of composing a function with itself some arbitrary number of times. That essentially allows us to commute or flip these two applications of the function so long as f is a function that takes inputs from a set and gives outputs in that same set. And the reason that we've been doing this along with doing proofs by induction and using sigma is we've actually been building toward defining addition, and that is what we're going to do today. And these constructs that we've kind of proven are going to help us identify and prove some useful properties that addition has, properties that we're already familiar with, but this will finally let us put on firm footing why it is that these properties do hold for all natural numbers. So let's begin by defining addition. We're going to define it like so. I'm going to define a plus b to mean that you take sigma and you apply it b times to a. And recall that sigma is indeed a function that takes a natural number as input and gives a natural number as output. And what is this definition saying but our grade school definition of addition, where you start at a and you count up b times, and the last number you land on is precisely the result of b plus a, or a plus b in this case. And the first useful property that we're going to prove that addition has is that it is associative. So associativity of addition. And this has to do with what happens when we add more than two numbers at a time. So say I give you two numbers a and b, and I tell you to add them, and then I tell you to add the result of that to c. Is that going to be the same? Is that going to be the same as if you had added b and c together first, and then added the result of that to a? Well, we're going to prove that it is in fact always true, and of course this proof is going to be done by induction, and we're going to induce on c. So our base case is going to be c equals 0. So what we really need to prove then is for all a and b in the naturals, show that a plus b plus 0 is the same as a plus, and this is of course trivial, but base cases and induction proofs often are. Alright, well, let's take a look at this term on the left here, bracketed in red. That is equal to, well, sigma applied 0 times to the result of a plus b, which is just the identity function, giving us back a plus b, whatever that is. Alright, now let's take a look at the right-hand side, which we will bracket in blue. That is going to be a plus the result of applying sigma 0 times to b, which we defined as the identity. So this is a plus, well, just b. And so these two expressions wound up being equal, and indeed adding 0 to both sides of an equation does not change the validity of the equation, regardless of how you group the parentheses. And that's what we've established here with our base case. So next we're going to move on to the induction step, where we assume that for all a and b in the naturals and some specific c in the naturals, that a plus b plus c is equal to a plus b plus c. Alright, as with all induction steps, we now need to show that this is true for sigma of c as well. And this is what I mean when I say inducing on c. So c is the thing that we assume is 0 in our base case, and c is the fixed value that we assume our proposition holds for in the induction step, and we're also then going to show that it continues to hold true for sigma of C. In other words, that A plus B plus the sigma of C is the same as A plus, and this time we're going to first compute what sigma of C is. We're going to add B to that, and then we're going to add all that to A. And we need to show that these two things will always be equal. As always, let me first bracket this in red and bracket our other side in blue, and we're going to carry out the remainder of this on the right side of the page here. So starting with the red side, we're going to use our definition of addition to re-express these two parts using sigma. And so this is sigma applied sigma C times sigma of C times to the result of A plus B. Okay, well, once again, using our definition of self-composition of a function some number of times, applying it sigma of C times is the same as applying sigma once to the result of applying sigma C times to the result of A plus B. Now we're going to regroup this with our definition of addition. So this input to the function is going to be surrounded by its own parentheses. And what is this asking but to add C to it? So this is sigma of the left-hand side here of our inductive hypothesis. And this is perhaps giving you a hint about what we're going to do next. Well, we're going to start with the blue side now. So now we're going to say, we're going to try to regroup these terms as well. So let's first tackle this parenthesized term right here. So we're adding sigma of C to B, and writing that with our definitions, we're going to rewrite this by saying that it is sigma applied sigma of C times to B. Once again, regrouping using the definition of addition. This is A plus, or rather using the definition of composing a function with itself some number of times, we're going to kind of pull this leading sigma down and rewrite this like so. Now we're going to regroup this term in here using the definition of addition that we've just given up above. So this is A plus sigma of, well, that's just B plus C in there. Now we're going to group this whole thing together using the definition of addition. So we're going to apply sigma of B plus C times to A. Okay? Once again, we can pull the leading sigma out, and this is applying sigma to the result of having applied sigma, this time only B plus C times to A. And now we regroup the term in here. So now you can imagine that this is really surrounded by parentheses, so that what the inside becomes is A plus in parentheses B plus C. All right, so we've transformed our both sides of this equation here. We haven't yet proven that it's an equation, so I'm going to scribble that out. We really just have two expressions here, and we've translated them both into sigma of one of the sides of our inductive hypothesis. You'll notice that this is the left, and this is the right. Now, by our inductive hypothesis, we assumed that, and I'm just going to rewrite it here for emphasis, we assumed that this equality is true, and that was because of our inductive hypothesis. But that implies that sigma of each respective expression is going to equal sigma of the other. And why is that true? Well, that's because sigma is injective. But then what we've really shown is that these two are equal to each other and so the original expressions must have been equal as well, completing our proof that addition is therefore associative. See you next time.